Let's take a look at torque. So the first part is that torque is R cross F, and it is a vector. R is probably best thought of as the lever arm, where F is the force. And so if you take some basic examples, take a pulley and attach a rope to it, and if you apply a tension this way, acting with the lever arm of R, then the torque, again, what does torque do? Well, you gotta remember, there's two equations that involve torque. Torque equals I alpha, and torque equals R cross F. This equation is how you actually find the torque associated with a particular force being applied with a lever arm. This is what the torque actually does. A torque causes something that has a moment of inertia to have an angular acceleration. In this particular unit on torque, we're going to be involved in equilibrium questions. So when you think of equilibrium, particular static equilibrium, we're looking at situations where the net force is equal to zero, meaning there's no acceleration, and where the net torque is equal to zero, which means it's not changing its rotational state of motion, which means most of, I guess, all of these cases, it's not rotating at the beginning, and so it's not rotating at the end. This would cause a net torque. Pulling this string down would rotate this pulley. And again, a pulley would have a certain moment, which would cause the pulley to have an angular acceleration, which means a changing omega, which means it would rotate. We're looking at static situations, like one rope is pulling here, and let's say another rope is pulling down here. And if you pull down the same, well, this would cause the opposite torque. So this tension will want to make the pulley rotate clockwise. This torque would want to make it rotate the counterclockwise, and they would balance each other. Obviously, if you pull harder on one side than the other, then you would have a net torque and it would rotate. But really, we're going to look at all these situations of what causes the torque. It's a force with a lever arm, and again, this cross product, don't overcomplicate that. It just means you want them to be perpendicular. Everything's about being perpendicular. If you have a door and it's hinged over here, how do you open the door? Well, you'd walk up to the door and you'd push perpendicular to it. Not only would you push perpendicular, is that you push a far distance away from the hinge, right? This is where the door is going to rotate. You'd want to push over here. Try opening a door really close to the hinge. It's really difficult because even though you're applying a big force, you don't have a big torque because you have a really small lever arm. What would happen if you took a force and you went like this? Well, you're not going to open the door, right? You could hit the door with a sledgehammer right here. That's not going to make the door rotate. You might smash the door, but it's not going to make it open or close because there's no perpendicular piece. The force is directed directly back to the pivot, which does not cause a torque, right? It has an R and it has an F, but there's no perpendicular piece that is shared by them. And then, of course, if you put the force right at the pivot, well, even though you could hit a sledgehammer on the hinge of a door and it's not going to open the door. You have a big force, but you have a zero lever arm, even if the force was somehow perpendicular, but it's operating directly at the pivot, so there's no lever arm. So this particular force would not cause a torque. This force wouldn't cause a torque, and that this would probably be your best way to maximize the torque on opening a door. You'd want to have, again, this distance would be your R vector. This would be your force, and those two together, and you would just multiply them because they are perpendicular. That would give you your torque. So let's look at a couple situations. Probably the most popular situation is one where we look at a wall, and then we'll take this board and we'll extend it this way. So this is some board with mass capital M. Let's go ahead and hang a box from it. We can call this little m. Let's go ahead and take a cable and stretch it to the end. So this is some cable. This is the wall. And then over here is the hinge. So there's a hinge that attaches the board to the wall. So we have the situation, nothing is accelerating and nothing is rotating. And so what we know is that the net force is equal to zero on the system and the net torque is equal to zero. The force is the easy part. We're going to look at both the x direction and the y direction when we look at forces. And let's go ahead and draw the forces first. Oops, I guess I forgot the E on hinge. So the forces here. So we have the center mass of the board has a weight down, which would be capital MG. We have the weight of our box hanging down, which would be little mg. We have the tension in the cable that we'll just call T. And then we actually have a force on the hinge. So the hinge, what it would do is that it really would push this way. Let's call that H subscript X for the horizontal hinge force, and then we'll call this HY. And you'd have to think about why they are those particular directions. But if you had a board hanging from a cable, if there was no wall, the whole board would swing that way, and the board would drop. And so the hinge functions to both keep the board horizontally to the right and vertically supported upwards. And so then let's just do forces. Again, this is just old school forces here. So what happens is let's balance the horizontal forces. This is some angle theta, and this is some hx. So hx is pushing to the right, t cosine theta is pushing to the left, and those have to be equal. And there's no other forces, right? Those are the only two horizontal forces, and we know they have to be zero because the system does not have a horizontal acceleration. And then in the y direction, we have t sine theta that's up. We have hy that's up. And then we have the board's weight and the box's weight that is down. And those have to be balanced. The ups versus the downs have to be zero. And that's kind of just an old school analysis of all the forces acting on that system. And then the new part is to look at the torque. Torque itself, remember, torque, each individual torque is R cross F. Take their force and then their lever arm. And so the first thing you have to do is choose the pivot. And we're going to make the pivot at the hinge. So pivot at the hinge. And you could prove to yourself that it doesn't matter where you put the pivot. You can put the pivot in a variety of spots and nothing's going to change. It's really a perspective thing. So if we put the pivot at the hinge, the beauty of that is both HY and HX don't cause a torque, because they operate at the hinge, and so they don't have a lever arm. So we don't even have to worry about those two things. So let's think about this. The cable. The cable would cause this board to rotate this way. Both the board's weight and the weight of the box would cause the board to rotate in this direction. And so let's go ahead and call the counterclockwise torque the tension in the cable, T sine theta times L. And you have to think about why I did that. If you break down the tension in the cable here, the tension in the cable is this way, and there's the lever arm, it's the whole length of the board, but not all of that counts. Only the vertical component of the torque, and that's T sine theta, actually causes the torque. Remember, we need a perpendicular piece to this lever arm. T cosine theta would be going straight back this way. And again, a force directed right back to the pivot is not going to cause a rotation. So that we don't have to worry about in this problem. It's just T sine theta times the lever arm of L, and that would cause a counterclockwise torque. And the two things that it's fighting against is little mg times its distance. Let's say this distance is, I don't know, 4/5 L. It looks something like that. That would have to be given to you in the problem. And then the board itself, capital MG, is at a distance L over 2. And that has to equal 0. And then we have our three equations, and we really have three variables here. If you look at all the equations, we typically don't know the tension, the horizontal hinge force, and the vertical hinge force. But what we can do is, this equation, the only variable is the tension. We know the length of the board, we typically know the mass of the board and the mass of the hang block, and we know the angle, and then we can find tension. And then once you know tension, you can come up to here and find the horizontal hinge force and use this equation to find the vertical hinge force. Again, once you know the tension after the torque, then you can use either of those two. And this is our classic kind of like the hanging sign problem. All right, next let's look at a ladder problem. And a ladder problem is still an analysis of torques and forces. So there's my ground. There's the wall. And then we have some ladder here. Okay? And it's fairly consistent that we're going to talk about having up here on the wall, there's no friction. But on the ground, there certainly is friction. We have to talk about why certainly that has to happen. Let's look at the forces now. So the forces, we'll draw in blue this time. There is a normal force exerted by the ground on the ladder. There's friction. You can make an argument of why friction has to push it that way. Again, the ladder without friction would tend to slide this way, and so the friction here would actually push it to the right. There's the normal force here. Let's go ahead and call this the normal force subscript y, and here a normal force subscript x, indicating the direction that the two normal forces are actually moving, right? This is the wall pushing this way, and this is the ground pushing up. And let's have a firefighter. Let's have the firefighter a quarter of the way up the ladder, and then let's put another dot to represent the weight of the ladder. So let's say there's a big mg for the ladder, and then a little mg for the firefighter. And those are the forces. And so let's look at a force analysis. Again, we have an equilibrium situation. So we know that both x hat and y hat, the forces have to balance. In the x direction, we have the force of friction. Has to be equal and yet opposite to the normal force that the wall exerts. And that has to equal 0 because we're not accelerating to the left. The up forces are n, y, and the down forces are both little mg and capital MG, and those have to be equal to 0. You do have to remind yourself that there is a relationship here that we know of. Remember that the force of friction that the ground exerts is equal to mu times the normal force of the ground. So we actually have a relationship here. The force of friction equals mu n. N, though, the normal force of the ground, is equal to mg plus mg, and think about that. Of course that's true. The normal force of the ground has to support the weight of the ladder and the weight of the firefighter. So then the force of friction equals mu times mg plus mg. But then the force of friction equals the normal force of the wall. So there, we can actually see that the normal force of the wall has to equal this. So we can do a couple of these things before we even look at the torque equation. So that's a nice view of that. The normal force has to equal friction. Friction is mu times the normal force of the ground. The normal force of the ground, though, has to be the weight of the two objects. All right, now let's look at torques. We are going to put the pivot here. So let's go ahead and put a red dot to represent. We are looking at the pivot there, and then we have to look at the torques. Think about what direction, if you took a string and you put it at the top of this ladder and you pulled the string this way, what direction would it make the ladder rotate? Well, it'd make the ladder rotate this way, counterclockwise. Well, what's the mass of the ladder and the mass of the person? Well, both of those things want to make the ladder rotate this way. So it's this torque is balancing these two torques. These forces don't appear in the torque equation because they don't have a lever arm. Remember, they are acting at the pivot. Torque, again, is R cross F. And if there's no perpendicular piece, there's no torque. And if there's no lever arm, there's no torque. These don't have a lever arm considering they operate at the pivot. So let's do this one first. So the torque of itself is the force times the lever arm. And this is where it gets a little tricky. If you have a horizontal force, the lever arm is going to be perpendicular. That's the perpendicular distance associated with that force. This distance is L sine theta. Okay? This guy, that's the force, and that's the lever arm. This distance is the perpendicular distance from the pivot. I mean, this is the true distance that force is acting, but it's not perpendicular, right? If you think about drawing that, that's what we have when we're looking at the big mg and r. But their cross product only takes this perpendicular distance. And so for that instance, we would say minus mg L over 2 cosine theta. L over 2 cosine theta gives this. L over 2 is this distance, L over 2 cosine theta is that. And then we do the same thing for the firefighter. And again, that's a little mg. And if he's a quarter of the way up the ladder, it's L over 4 cosine theta. And again, the torques have to be 0. And so if you look here, we can take this value and plug it in there. And then it would just depend on the question, whether the variable you want to solve for is mu, that the only variable here would be mu, or maybe you wanted to figure out the mass of the ladder, or the mass of the person, the angle that you could set it if you knew everything else. And so it would just depend. But in general, you're still going to set it up. You're going to look at the two force equations and a torque equation. And then this relationship is just true from basic kinematics at the force of friction. Its maximum value is mu n, and we typically are looking at the max. And so this is our firefighter problem. The last one I want to look at is a strut problem. And in a strut problem, what you're going to do, let's say you just don't really have a ceiling to work with. So here you have this ground, and you have this wood strut that's angled this way, and you're going to hang something from it. And then hopefully you can understand that this would be impossible to balance. This would be a ton of force necessary there. So, you know, you could support it this way to some ceiling, but let's say you don't have a ceiling to work with. And so what you do is you take a cable, this is the cable, this is the strut, and you could provide some extra force to pulling it this way. Okay, let's draw forces on this thing first. So there's the weight of the strut down, so there's some mg there, there's some mg from the hanging weight, and there's some tension back, right? Those are the forces acting up there. And then down here, we do have a normal force in this direction, call it Ny, and then we do have some Nx. We are going to put our pivot here, which I think is fairly predictable. And then we're going to do the same thing we always do. We're going to say that the system's in equilibrium, so there's no net force and no net torque. And so let's balance those things. So as far as forces go, in the x direction, we have Nx is pushing it to the right, or holding it to the right, and then t cosine theta. And we have to be careful here. This we'll call theta 1, this we'll call theta 2. This angle, again, t cosine theta is that guy, and it has to do with the red angle. The angle of depression and the angle of elevation are the same. So that's t cosine theta 1, and those are the only forces pushing to the right and pulling to the left. So those have to be equal. And then in the y direction, we have Ny minus mg minus capital Mg. And then if you look at t sine theta, it's actually down, right? The red, the cable, is pulling left, but also pulling down. So we need to do a minus t, and again, this one is also sine theta 1, and that has to also equal 0. So we have two force equations, but there's a couple of variables there that we don't know, typically t, nx, and ny. So now we have to write the torque equation. Okay, and when we look at torques, we're going to use this as our pivot, so that neither of those two forces cause a torque because they don't have a lever arm. And then the hardest part is this cable. So we know that the cable's tension is down, but I would draw it like this. Think of one, the horizontal force going that way, and then draw the vertical force this way. This is t cosine theta 1, and this is t sine theta 1. Those are the two forces. And if you think about the horizontal thing, if that's our strut, if you pull horizontally this way, it would cause this rotation. And if you pull vertically down on that, it would actually cause this rotation. And so t cosine theta 1 is this force, and it has this lever arm. This distance here is L sine theta 2. This distance is L sine theta 2, or this is theta 2. And that horizontal force goes with the vertical lever arm, and that would cause a counterclockwise rotation. All the other ones, both this tension, this weight, and this weight, all want to make this thing rotate and down. So they're all minus signs. So we have t sine theta, oops, that is a sine theta 1. That's a 1, sine theta 1. And if that's a vertical force, then we need the horizontal lever arm, which is L cosine theta 2 minus mg, the box, and it's operating at the exact same spot, so it's got the same lever arm, cosine theta 2, and then minus the board itself, which is, we'll say, capital Mg, and it's got a lever arm of L over 2 cosine theta 2, and that has to equal 0. I know I kind of ran out of room, but these three torques all want to make this thing rotate clockwise. This torque wants to make it rotate counterclockwise, and all the torques are R cross F. They're forces with perpendicular lever arms. That horizontal force, vertical lever arm. These are all vertical forces, and those are their corresponding horizontal lever arms, which, as you can see, I used cosine with those. And if you think about this right here only has tension in it. I know it's a long, crazy equation, but the only variable is tension. Once you know tension, you can use this to find nx and this to find ny, and then you would know everything you wanted to know about this particular setup. Okay, so the main three, again, there's a variety of questions, but the main three problems that they love to ask about torque are the hanging sign problem, the ladder problem, and then this strut problem. We can look at additional problems. You know, I think in the homework somewhere we looked at, you know, a diving board situation or anything where there's, you know, something here, there's a box here, and the question is, well, how do you support it? Well, just think about this in the real world. There's some normal force here that has to support this vertically. This is some weight down. If you looked at this as the pivot, this mg operating at some d, that would cause a torque, right? That particular torque, we'll call that torque 1, would be mgd. And it would cause a clockwise rotation. Well, you have some choices here. Lots of choices, actually, but two of the main choices are, well, what could you do over to this end? Well, you could put another box here. And it wouldn't have to be the same mass. It could be a bigger mass, and this could be like d over 2. Well, then how would big mg have to compare to little mg? Well, if it's half the lever arm, it'd have to be double the mass to make it have the exact same torque. Or you could actually, instead of putting a weight there, you could nail it down and push this thing down. Again, pushing it down is the same thing as pulling it down. You could just put, you know, you could bolt it into the, if this was some, you know, diving board situation, there could be the fulcrum. And imagine that the whole thing is some platform here. And again, at the end of the diving board has bolts in it, and it's holding it down, it's pushing it down, so that when you walk out here, dum, 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 and you're out to the end, the whole diving board, and if it wasn't nailed down, would just tip. And so you nail this down, which causes a torque in that direction, and then you're allowed to come out here. And again, you can have any of these situations. You can have a disc, which is really a pulley, and you can pull on it there, and you can pull on it there, and you can attach another rope and pull there. And again, these two would both cause a counterclockwise rotation. This force would cause a clockwise rotation, and if you know the pulley isn't rotating, all the torques must be equal to 0. And again, they all wouldn't even have to be in the center. You could put a nail right here, and you could pull up right there, and that would cause a torque, and it would just have a different lever arm, right? Take the pivot, which is the center of the pulley, go out to your force, and then look at the perpendicular piece, and then find the torque. Again, all torques are of the form R cross F. Find the lever arm and make sure it's perpendicular to the force. And again, if it's not perpendicular, then you typically are going to take some cosine or some sine piece of it. If they are perpendicular, then you can just multiply the two together. And if you have a situation like this, where that's your F, that's your R, well, they're already perpendicular, right? The force of the string is indeed tangent to that circle. Okay?